This is a note recap of the day one set of notes from chapter 16, where we get into acids and bases. Now, chapter 16 is an application of equilibrium chemistry, and we look at equilibrium as it applies to acids and bases, as well as some non-equilibrium situations. But this is a pretty hefty chunk on the AP test. On the legacy exam, the old version of the exam, typically about 10 of the 75 questions came from acid-base chemistry, and it was pretty much in the FRQ every single year. So this is definitely an important application of equilibrium that you should understand. Now, the first thing that is really important for this chapter is that you memorize the strong acids and bases. This is something way back from chapter 4. One of the earliest things we did in the class was memorize these. You have to know them for this chapter. There's so many situations where that becomes very important. So remember, the 7 strong acids and the 8 strong bases, you have to know them cold. Another thing that sometimes students mistake is they talk about conjugates as differing by a hydrogen, but it's not really a hydrogen, it's a hydrogen ion. HSO4 is not the conjugate of H2SO4. HSO4 doesn't even exist. It's HSO4 negative. It's the anion, what you get after you lose an H plus from H2SO4. And that negative is important. So be careful with conjugates. Remember, it's 2 things that differ by an H plus, not an H. Now, one of the diagrams that you're going to use in the first set of homework is this one. And really, problems 22 and 26, remember, you're just going to be doing straight questions from this set. One of the most important things about this is the relative strengths and how a substance's conjugate is the opposite, and the strength of one is related to the strength of the other. The stronger the acid, the weaker its conjugate base. The stronger the base, the weaker its conjugate acid is going to be. And that's an important idea because it pops up in several different places. And here's another situation where you have to know your strongs. When you have a strong acid, because I ionize 100%, you form a negligible conjugate base. In other words, it doesn't really act like a base, because in a strong situation, it's pretty much a single directional reaction. Another reason to make sure you memorize and know your strongs. In any acid-base reaction where you have acids and bases by Bronsted-Lowry on each side, you really need to understand that it's all about who is better at acting like a base, because you have a potential base on both sides. In this case, water could take the proton from HCl, and in the reverse, Cl minus could take the proton from H3O plus. So we basically have 2 competing bases. The reaction that is going to move the proton more is the one that has the stronger base. So the stronger base is going to win. And if you take a look at the whole idea that we talked about strongs and their opposites being negligible, Cl minus isn't even acting like a base. So while H2O is a weaker base, it still is acting like a base, and Cl minus doesn't. So therefore, H2O is a much stronger base than the 2. In fact, it's so much stronger that for all intents and purposes, Cl minus isn't grabbing any hydrogens, so this would have a massively huge K, so big that realistically we write it as a single directional reaction. We don't even talk about it from an equilibrium standpoint because it's not really relevant. All of the strongs work that way. Their conjugate that they create is going to be a negligible base. So therefore, no matter how weak the base is that is with the strong acid, it's going to function as a much stronger base than the other side. And that's one of the reasons why we draw strongs with a single arrow when we talk about dissociation. Whereas when we have a weak, we always draw it with a double arrow. Because in this particular case, both of these bases function as a base. Now, sure, one is stronger than the other, but they do both function as a base, so this is a 2-directional reaction. But acetate is the stronger base than H2O, so the equilibrium should favor the reactant side. In other words, K should be less than 1 in this particular case. And that's because acetate is the stronger base than H2O is, and you can see that from the table. So remember, the stronger base wins, and that has an impact on the situation.